What's up, everyone? It's me, Miss Wesley. It is calc time yet again. We're in integration by parts packet, starting at the top of page 3 for day 2 on this topic. A joke for you to start. Why wouldn't you trust your math teacher if she's walking down the street with some graph paper and a pencil? Because she's probably plotting something. Now let's get into this. I want to set ourselves up for number 3. I know we had worked on a couple examples the other day, but I want to see if we can make a little bit more sense out of this whole method. And you should especially look at a problem, decide that there's not some easy integration method you can use. Even use substitution would probably fall short for us here, wouldn't make enough stuff cancel. And once we decide we're in this product situation of an integration by parts, we want to write the formula by each one of these problems. So here's the formula. It's the integral of u dv is what we're trying to set up, and it gets to equal uv minus the integral of v du. So here goes, and we've got some jobs to do. We've got to pick a u that would be smart, and we've got to pick a dv out of the stuff that you see here. Now you'll notice on this page in 3, 4, and 5, they each have a little measly x sitting out front. And a lot of times x is a really good choice for you. And we'll talk about why it may or may not be the best choice in this situation. So I want to set it up with a u and a dv. So there was this suggestion for picking u if you want to choose that first here, and it was that you can choose something where its derivative gets simpler than itself. So if you choose just x, it's a pretty safe choice because its derivative is just 1, and that's definitely hands down simpler than itself. If you had picked cosine of x, I mean, its derivative is negative sine. It's a different trig function, not necessarily simpler. It's also smart to let the cosine part of it, let the trig function go into the dv part, because we have a good basic integration rule for this. And it is the more complicated, I'd say, of the two expressions. Is there one thing I forgot? There's one little thing. I've scooped up the x, I put it in this part. I've scooped up the cosine of x, I put it in that part, but I forgot about the dx. The rule is whatever you put as dv gets in dx tagged on the end of it. So now all 3 parts of this are accounted for, and we've got it in the format of the left-hand side. Next up, let's keep this organized so you have a method that's going to work for every single one of these. We do some side work. The side work involves, for u, it involves a derivative. For dv, it involves an integral of both sides. So for u, let's take a derivative. Du dx equals, we mentioned it was going to be 1. And because we're going to need to plug in for du, let's get this solved for du. So du actually in this case equals the same thing as dx. We're going to use this, and I think we're going to use this as well. So 2 pieces to a puzzle. Next up, we have dv equals the cosine of x dx. The way to get this to be just v is to take an integral of both sides. Can you squeeze that on there? Integrate the left side, integrate the right side. And you do get a v here. This is like saying the integral of the number 1, which is v. On the right side, integral of cosine of x, what function has a derivative of cosine of x? That's just going to be sine of x, technically plus c, but we're saving that for the end. Now I've got the puzzle pieces. I should be able to go to this fancy integration by parts formula and get this thing solved. So first it says to put uv. So what is u? U is x. V is sine of x. So that's part 1. Minus a part that we're going to have to simplify, the integral of v again. So v was sine of x. And then sub something in for du in terms of x, it equals dx. And I think we've got it. Keep the first part how it is. X sine of x is good to go. Minus the integral of the sine of x, the function whose derivative is sine of x. Well, that would be negative cosine of x. And plus c, so we don't forget it for later. Let's just make this a plus in the middle too. So x sine of x plus cosine of x. Where we have time for it, it is really good to check these solutions by differentiation. We can check this by taking the derivative. So I'll say derive your solution and see if you get this expression back in the end. And this will always involve a product rule. So product rule for starters, been a while, f prime g plus g prime f. So derivative of x times regular g part, sine of x, plus in the middle of a product rule, and then derivative of sine of x times regular x. So x, sine's derivative, cosine of x. So that's the first part. Plus the derivative of cosine of x, so that's negative sine of x. And the derivative of c, that's a constant, it's just going to be 0. Is what I wrote in green here equal to the original? Well, it certainly is, right? You have positive sine of x minus sine of x. All you have left over is what you started with. So where other techniques failed, integration by parts got the job done. The questions get a little bit more interesting as you go, scroll down the page. I do want to take a look at number 4 now. So this one says, we've seen one kind of like it, but this one's more interesting because the e isn't just to the x power, it's to the 2x power. We can still structure this problem the same exact way. So let me get myself set up notation-wise. We want to write this so that it's going to equal the integral of u dv. And we're going to do that by selecting a y is u choice and selecting a y is dv choice. And integration by parts, just so that we have it for later, the formula says it equals uv minus the integral of v du. Okay, so this is what we're working on. All right, what are you going to make u? Now, I kind of gave this away in the last problem by saying x is usually a really good choice, but it is a good choice. Its derivative is simpler than itself. The e to the 2x is both more complicated and able to be integrated with a basic integration rule. So it's probably a good idea to put that here. With the dx we mentioned, that also has to get written in that expression. Okay, same side work. I hope you're working yourself into a rhythm now. Like, I'm hoping some of these steps become repetitive within the next couple problems. These steps are going to be deriving, so du dx equals 1, and just like last time, du equals dx. So we've got 2 usable puzzle pieces to bring back to this part. Now the side work that involves integrating. Can you squeeze in an integral sign on both sides? We want to integrate the left, so integral of 1 dv just equals v always. This part can be done with u substitution or done really easily with a guess. If this had just said e to the x, wouldn't you say its integral is e to the x? So I want to make a guess here. I'm guessing that maybe the integral of e to the 2x is e to the 2x plus c. Almost, not quite. So now let's check our guess and refine it. If we derive this, do we exactly get this back? So if I took a derivative of this, I get e to the 2x, but chain rule says I have to tag on an inside derivative times a 2. And that's not what the original said. So we have to think of a number to put by this that will cancel with the 2 and become the number 1. So you have the original back. So that's an easy fix. Slide a 1/2 out front. If you also divide by 2, now when we check this times a half, you have the original function back. It checks out. So 1 over the derivative of the inside, e to the 2x, and you have that part. I'm going to just circle this and actually circle the problem. Because of that discussion in blue there, this one takes, a little bit more attention just to make sure you have the puzzle pieces right. Okay, time to go back to this formula. I think we're good to go. What is u? U is x. What is v? V is what we circled here, so 1/2 e to the 2x, which is going to get used again in a second. Integral of v, so 1/2 e to the 2x again. And then du, where are you? You're over here. We can write dx. Okay, so we're almost set. We've got a little bit more simplifying to do, but that's not a big deal. We'll leave this first part. Maybe I'll just write it as x over 2 e to the 2x minus, now we're going to integrate this again, right? Work your magic here. Let's see what we can guess. Well, the rule says we've got the 1/2 that was already there. We're guessing it is its own integral, the e to the 2x, but we need the 1/2 to slide out and be part of it. It's actually going to be 1/4. Let me rewrite. X over 2 e to the 2x minus 1/4 e to the 2x, right? 1/4 e to the 2x should have that as its derivative, plus c and plus c. Because of all this e discussion, and just in case it helps, there is a rule that I give you from time to time. E to the x, its own integral. What could be better? E to the x plus c. If it's e to the anything else x, e to the kx dx, feel free to use this rule. What we saw a couple times in this problem, it's 1 over k e to the kx plus c. It's another couple rules that you can use. Again, like I said, these get better and better. We're going to try one more. We're going to try number 5. Okay, give this one a double star. It's probably the best one we've tried yet. Okay, same deal though. There's a little x sitting out front. I have this sinking, sneaky suspicion, I guess, that u is going to equal x again, but that's just me. Go figure. Let's say, okay, if this is going to be a u substitution question, we have to get it in the format integral of u dv equals uv minus integral of v du. Okay. And let's see how this works. We need to figure out a u. I'm guessing it's going to be x. We need to figure out a dv. My guess is it's going to be square root of x plus 5 dx. That's just my guess. Let's talk about why these would be good guesses. Number one, does u look good? I think it's the simpler part, and its derivative is 1, so it's simpler than itself. Now let's look at the dv part. To me, this is the more complicated part of the expression, and we can easily follow a basic integration rule to integrate both sides and get this thing simplified. So let's go with it. If we made the wrong choice, we could always switch what we wrote. Here goes. Take a derivative for this part. I feel like I've done this a lot today. So du over dx equals 1 and du equals dx. So not too surprising, that left-hand side. Now let's be really careful with the integration, and we might want to do a rewrite here. Integral of both sides, let's do a rewrite. You want to integrate 1 dv, so we know that's actually just going to be v. We want to integrate this thing. Let's write what power it's to. X plus 5 to the 1/2 power dx. And again, this problem could be its own little u sub problem, but just like in number 4, I want to do this in a quicker, more convenient way. I want to see if we can guess a solution. If it had just said x to the 1/2 power, what's the integral? Well, you would know what to do with the powers. You would have said x to 1 power higher, 3/2, divided by that 1 power higher. So we'll put a 2/3 out front. Well, it wasn't just an x that we were raising to the 1/2 originally. It was an x plus 5. So can we put that in there too? X plus 5. And then there'd be a plus c that we're not really addressing right now. Check your guess. See if your guess, if you take a derivative of this, see if it's going to give you that back. And if it's not, we can divide by something like we did last time. But this one should work out. A power rule, chain rule derivative is you swing the power down, you get a 1 out front if I'm checking. You have x plus 5 to 1 power lower, so to the 1/2. You take an inside derivative, chain rule, but this time it's just 1. So it checks out. You have this original back. This is your antiderivative of x plus 5 to the 1/2. I'm just going to circle it because we're going to use it twice. And we'll work with this integration by parts formula. Okay, so one more time, checking this out, start with uv. So u is x. V is this thing that we circled. So x times 2/3 x plus 5 to the 3/2. Okay, minus integral of v du. So here comes v again. 2/3 x plus 5 to the 3/2. And du is equal to dx. So we can write a dx there. And this is what we're looking at. So this part's pretty much going to stay the same. I might just flip-flop the order of these. And this part needs to get integrated. So let's do just that. I'm going to make it, I'll put the 2/3 x first. So 2/3 x plus 5 to the 3/2 minus. Okay, so now let's make this convenient for ourselves so we don't have to do a u sub. Leave the constant 2/3. Make a guess, right? If this were just an x, we'd say, okay, x to what's 1 higher than 3/2. So 3/2 plus 1 gives you 5/2. We're going to divide by that 5/2 and make it 2/5. What are we going to put inside? We're going to put x plus 5 inside. And then don't forget the plus c at the end. Do we have to amend this guess at all? Does it look okay? Well, actually, it should work out perfectly. If we took a derivative of what I just squiggle underlined, the 5/2 would cancel with the 2/5. You just have the 2/3. And then this thing would stay, and it would be down a power to the 3/2 power. We get kind of lucky here because your inside derivative is just 1. So nothing to divide by, nothing to change. This thing is set. We can just multiply those two coefficients and call it a day. So here's your first part, 2/3 x plus 5 to the 3/2, minus, let's make this 4/15, x plus 5 to the 5/2 plus c. This deserves some sort of maybe giving yourself a pat on the back or me giving you a virtual handshake. These are some of the most complicated antiderivatives we've ever taken before, and integration by parts is what's really going to help. So I hope we get more use of the pattern in the days to come, and I hope you really enjoy the rest of your day. Talk to you soon.